Yeah, thank you for the invitation to speak about sleep as well as the National Sleep Research Resource. So what I'm going to do is I've divided the talk in a few different chunks. First, I'm going to give a bit of an overview of why you should be interested in sleep and circadian measurements if you're a researcher in metabolic health. So I'm going to actually describe a bit of how we approach sleep and its multiple dimensions, and a bit about the background data that supports associations between sleep with glucose metabolism and diabetes. I will then talk about what the NSRR, the National Sleep Research Resource, is about, what we aim to do, how we function. I will highlight some relative databases, including some examples of studies that have supported publications addressing the interrelationship between sleep, circadian rhythms, and glucose metabolism and diabetes, and identify, ongoing efforts to link our resource with both TopMed and Biodata Catalyst. And I hope what I will do is leave you with some notion about opportunities that you may want to do to access sleep and circadian data to better understand metabolic health. So let's start with sleep. And you could probably tell by the enthusiasm in my voice is that, I and my colleagues believe sleep is in fact the fourth pillar of health. And although for years we recognized nutrition and physical activity and stress, we really can't, those three pillars are also highly interrelated with sleep. And in fact, when we think about the American Heart Association, which up until last year talked about life's simple seven, even the American Heart Association, based on emerging data, has expanded that seven to life's essential eight. And you could see with this arrow here, the eighth item is actually healthy sleep. Moreover, interest in sleep really is reinforced by the high prevalence of insufficient sleep in the population, and particularly the disproportionate prevalence of poor sleep in individuals from low-income communities or minoritized communities who are otherwise at risk for metabolic diseases and other health risks. But I want to also leave you with this notion, and I imagine there's a number of data scientists on this call, is that sleep is not simply a measure of how long you spend sleeping at night, but in fact, we know it includes multiple dimensions that not only include sleep duration, but when you sleep, the rhythm that you sleep, how robust your 24-hour rhythm is, how consolidated or conversely, how fragmented sleep you have, and the depth of sleep, the extent to which you get into deep sleep or light sleep. And in addition, sleep is characterized by precise neurophysiologic signals, the EEG, in EMG, that tells us about really brain activity at night. And we can also characterize sleep by the presence or absence of a sleep disorder like sleep apnea or insomnia, and its daytime sequelae like sleepiness and functional impairment. And again, from a data science perspective, I want to emphasize that sleep is not simply measured by a simple questionnaire item, but we have commonly used tools that are able to measure really sleep at multiple scales of measurement. So we have polysomnography here on the left, which collects multiple signals. As you could see, these are electrodes that are measuring brain waves and chin EMG and breathing and ECG. And here's a snippet of a 30-second picture of EEG sleep and a 5-minute picture of breathing during sleep. And then we can scale sleep measurement across multiple days, in fact, over months and years, using devices called accelerometers or actigraphs, and now even commercial wearables. And by measuring movement parameters during the 24-hour day over multiple days, we could characterize sleep, and its regularity and consolidation. And finally, we have a number of validated questionnaires to measure patient-reported outcomes, also at different scales: prior day, a week of sleep data, and different dimensions like insomnia or chronotype or perceived quality. So polysomnography, which actually our resource really focus is on, is considered the gold standard. It really is this collection of second by second data from multiple electrodes, including those that measure the EEG, as I said, EEG, EOG, but also ECG, respiratory effort, oxygen saturation, leg movements. And here, for example, on the right-hand side, again, is a little snippet, and you can see again on the top of this panel, there's measures of brainwave, then you could see the ECG. You could see here in the middle panel, these are bursts of leg movements, and then the bottom panels are different respiratory indices. Now, for quite a long time, we in the sleep community, before there were more powerful data and digital tools to analyze these data, we collapsed these data into very simple summary metrics. So, for example, below this here, you see what's called a hypnogram. And what a hypnogram is showing you is just simply the distribution of times in different sleep states or stages, from wakefulness on the top to REM sleep to deep stage 4 sleep over the course of a night. And in this particular case, it gives you a picture of sort of an individual moving from wakefulness into deep sleep, and then periodically having these cycles of REM sleep in blue, and then in gold, waking up periodically. But this is still pretty gross, although it gives a lot of interesting structural information about sleep. We call that macro architecture. But in fact, you could take the EEG data and you could express this as power frequencies. And here, for example, is the same overnight, just focusing on the EEG, really looking at really a different power spectrum. And then that could further be collapsed and translated into stages on the very bottom. But you could see this can actually provide a richness of information that really allows a number of different measurements, as I'll show you later, to be pursued. And here is actigraphy. Again, actigraphy is a grosser measure than polysomnography, but has the advantage of being able to be used over multiple days. So by measuring things over multiple days, you could enhance the representativeness of the data or the reliability, giving estimates in any given individual of their duration of sleep, their efficiency, how fragmented sleep is, their circadian or sleep-wake timing or regularity. So again, here on the left, you could see an individual here. Each row is a different 24-hour period across a week. And when you see this black marks, these are individuals. This is movement, so that's wake time. And then this area in blue, you can see little movement, which is their sleep period. So this is someone who's getting very regular sleep. They're going to sleep the same time, waking up the same time every day with few sleep interruptions. In contrast, on the bottom, you see a very different pattern with this individual going to sleep at very different times. And here, for example, on Saturday night, we have maybe a 3, 4 in the morning sleep onset, and also some, more sleep interruptions. And you could actually, again, represent this. So there's a good sleeper here is in the middle, is being shown is getting, 7, 8 hours of sleep with consistent timing. And really an individual with a lot of sleep variability, you could see differences in the onset and the offset of their sleep period. You could also plot the data in a way to see if individuals have a very steady pattern over time, whether their sleep is generally shifted to go to sleep earlier. It's called a phase shift, or later, or in fact, if they lack circadian control or don't get light entrainment, whether they actually what we call free run, so they shift progressively. And you could also plot this according to fragmentation of sleep. And then we have a variety of questionnaires, and we could measure general sleep quality or your chronotype, your morningness or eveningness, your propensity for sleep apnea or your insomnia severity, your symptoms of restless legs. And you could even, when we had diaries and logs, to also look at self-reported sleep patterns in association with other exposures. Now, the major clinical sleep disorders that we think about are insomnia, which may occur in about 15% of the populations. And that is really a disorder characterized by problems getting to sleep or staying asleep, or sleep apnea, which may vary from the latest estimates, maybe 9 to 37% of adults, which is when I'll talk about that disorder of breathing at night, or periodic limb movements, which is recurrent leg jerks at night that disrupt sleep and cause arousals and autonomic surges, or circadian rhythm disorders where your sleep-wake patterns are really shifted or irregular over time. I'm going to highlight sleep apnea for just a moment because it has somewhat unique exposures compared to some of the other sleep dimensions I talked about. And in this disorder, you could see on the bottom, the individual experiences nightly problems with breathing during sleep, with really collapse of the tongue and soft tissue when they assume a recumbent position and neuromuscular activity goes down. And by not having an open upper airway here, you'll have these breathing pauses that we call apneas, or cessations of breathing, or partial cessations called hypopneas. And these changes will cause desaturation. So here is a snippet from a sleep study just showing the breathing being nice and regular with constant oxygen levels in a normal range versus the person who's having recurrent apneas with deep desaturations. And this pattern of desaturation it creates exposures to what we call intermittent hypoxemia, which may stimulate autonomic certain nervous system changes, inflammatory responses, oxidative stress, endothelial dysfunction, and insulin resistance. Now, if we look at the evidence linking these various sleep exposures or sleep disorders with metabolic disease, there's a very rich literature of human and animal experimental data that have shown that sleep deprivation or sleep misalignment, meaning you sleep at times that are misaligned with your circadian clock, or intermittent hypoxemia, as in sleep apnea, may actually stimulate the release of certain inflammatory proteins, alter gene expression, as I said, cause endothelial dysfunction, dyslipidemia, and alter glucose metabolism. And those have been shown in very nicely controlled experiments. And I'm an epidemiologist, and in our epidemiologic data, we can relate, extreme sleep duration, short or long, or sleep variability, as I mentioned, going to sleep and waking up different times across the week, or reductions in the depth of sleep, particularly the depth of slow wave sleep. And slow wave sleep is when parasympathetic tone is the highest and sympathetic tone is the lowest. That is associated with many metabolic processes or sleep apnea. And each of these exposures, and I'll summarize some of this, is associated with a wide range of cardiovascular outcomes, but for this audience also includes metabolic syndrome and diabetes, as well as problems with quality of life and mood and behavior. Now, this focuses a bit on the relationship, again, of sleep apnea with insulin resistance and diabetes. And again, just to emphasize, the intermittent hypoxemia plays a role, as does sleep fragmentation. But I also wanted to point out this could even be this bidirectional role where insulin resistance may promote weight gain, and weight gain in turn will exacerbate sleep apnea. And this slide now similarly shows the potential mechanisms leading to short sleep duration with cardiometabolic disease. So you could see that short sleep duration may trigger abnormalities in multiple pathways, including inflammatory pathways, appetite hormones, oxidative stress, but particularly as it relates to diabetes, increased sympathetic activation will actually reduce pancreatic beta cell responsiveness, reduce glucose tolerance, increase insulin resistance, and lead to diabetes. And again, there are separate pathways in terms of appetite hormones that will also increase obesity that are a function of getting insufficient sleep. Now, I think we all know that circadian biology is fundamental to really optimal physiological function across multiple systems. And here I just want to emphasize again, we have a central circadian clock in this suprachiasmatic nucleus, and that is very important for our control of our sleep-wake or rest activity cycles, which then in turn influences the timing of when we eat and our body temperature. And through those effects, there's an interaction, and those effects then may influence what we know now as really dozens of peripheral clocks that also occur through the system and influence gene expression across the 24-hour day, including clocks in the liver, the muscle, and the pancreas that are important for glucose metabolism. And in fact, now we know that disturbed sleep-wake patterns and really misalignment between your central, between your circadian system and the external environment, and interactions between your central and peripheral clocks can all lead to abnormalities in metabolism. And here is just a brief, again, summary that emphasizes one of the areas of sleep that I'm most interested in, which is sleep irregularity. Again, that's shown on this bottom slide, showing that, how the individuals who are going to sleep and sleeping at different durations across the week, again, to emphasize that this pattern may actually cause circadian disruption, influence dietary timing and content, inflammation, the hypothalamic adrenal axis, autonomic dysfunction, and even gut dysbiosis with really changes in the microbiome that then leads to inflammation and endothelial and other abnormalities. And then finally, this is just a nice slide from Lancet Diabetes that puts some of this all together, really emphasizing that our brain itself is the generator of and reciprocal in response to poor sleep, as well as circadian influences. And in fact, that when in fact there's reduced sleep, poor sleep quality, dyssynchrony or misalignment, there's multiple signals that are released that influence endocrine systems and influence lipids, metabolism, satiety, as well as effects on autonomic nervous system signaling on the stress axis, muscle sensitivity to insulin, and beta activity, beta cells. Now, how important is sleep relative to other risk factors for risk of getting diabetes? Here is one meta-analysis that compares a number of sleep-related traits to two traditional risk factors, overweight and family history of diabetes. And these are the relative risks of developing incident diabetes across these meta-analyses. And you could see difficulty maintaining sleep, which is a sign of poor sleep quality or a key symptom of insomnia, is almost as strong as family history of diabetes. And similarly, difficulty maintaining sleep, similarly, difficulty initiating sleep. These are both insomnia symptoms. And then sleep apnea, again, is not far behind with about a 50% increased risk. And then shift work and short sleep duration is also associated, but it's somewhat lower levels. Now, I also wanted to say that there's many opportunities to understand dose-response relationships. So here we see a meta-analysis really emphasizing how little we really know about this dose response in terms of underlying mechanisms. So we see that overall across meta-analyses, there is a significant association between short sleep, usually defined by less than 6 hours of sleep a night, or long sleep, often defined by more than 9 hours hours of sleep a night, with an overall here relative risk of about 1.09 for the short sleepers, 1.14 for the long sleepers, and a very, prominent U or J-shaped distribution of risk of getting diabetes according to short sleep or long sleep. But again, a lot of these mechanisms, especially with long sleep, are not well understood. Moreover, my colleague Qianyi Huang has been analyzing data from the health professional studies and MESA, which is in NSRR, and have shown that not only does sleep increase the risk of diabetes, but in fact, diabetes increases the risk of sleep apnea. So there's a bidirectional association, and I showed you one possible pathway before, and it may be through, insulin resistance that then also may drive weight gain, but also particular fat in the tongue, which may in fact impact the upper airway and increase the risk of sleep apnea. So this section of the talk, I just want to briefly summarize, is that I think I've shown you that sleep and circadian disruption are common in the population that are associated with obesity, insulin resistance, and diabetes. And the different traits that I reviewed are insomnia symptoms, long or short sleep, irregular sleep, also shift work, as well as low abnormalities in sleep architecture, or low slow wave sleep. And I also pointed out that the hypoxemia associated with sleep apnea also it has particular impacts on the pancreas, but also some of the comorbidities for diabetes, like diabetic microvascular complications. And in fact, very well controlled studies show that you can improve insulin sensitivity with treatment of sleep apnea. But again, there's complexity with a potential bidirectional association. So there's some knowledge gaps I'm hoping you're starting to think about based on this very cursory, very rapid summary of the literature. That is, how variable are these effects in the population? Do they vary by genetic background, gender, sex, discrimination, lifestyle? What really are the causal and the bidirectional mechanisms? How do multiple sleep circadian related stresses impact glucose metabolism, interact with other lifestyle and risk factors? And what can we do to really take advantage of the fact that during sleep, there's a tremendous amount of crosstalk between the various physiologic signals in our systems in our body that can actually be measured using existing technologies, and maybe that crosstalk is key to understanding some of these links. So here is really the opportunity that NSRR has tried to really promote, is that, as I mentioned before, most of the data sets that you might go into NIH repositories have simple summary data of how much time you sleep. If they have any sleep data, there's simple summary data, how much time you sleep, how much time you spent in REM sleep. But as I was saying, there's very, very rich data that has very precise temporal features, are able to look at dynamic features across the different channels from brain to breathing, and tools now that allow us to quantify really these signals in a way to characterize these different behaviors. And so here's an example. We could take EEG, and we could, as I said, we could look at power spectrum across the night and the variations in REM and non-REM sleep. We could look at the variations in particular features like here, slow wave activity, or even from breathing, we could actually begin to characterize and quantify things like hypoxic burden. So rather than just a simple measure, we could really look at the patterns of hypoxemia at night. So now let me introduce you to the National Sleep Research Resource, with hopefully that motivation for you to want to access sleep data. We built this and launched this in 2013 and designed this to be a community research to deposit and access sleep data that specifically includes physiologic signals and makes it easy to access those signals. and we focus on polysomnography and/or actigraphy, as well as sleep questionnaire data, but we also ingest and make available a wide variety of other data that is variable across data sets according to ownership and availability, but includes demographics and anthropometry, medical history, blood biomarkers, cardiometabolic indices, physical activity. And in the last year, we've been starting to ingest data from animal experiments, and you'll see we have some non-human primate data, and we're soon going to have hibernating bear data, and we hope to have mouse data soon. And we also recently have ingested human circadian data. And through my the co-director, Dr. Sean Purcell, we also have access to many powerful open source tools that he's developed and community engagement. And our focus is to really empower the wider community to browse, search, and download sleep data, and and when possible, using harmonized terms for core variables to help with standardization and interoperability. And this is a slide Dr. Purcell's created that I think says a lot, in that our repository is not just a collection of well-curated data sets, but we really try to support discovery in the community. And we want to do that by providing detailed documentation or useful documentation search capacities to actually do a lot of the upfront harmonization and standardization, providing metadata following both FAIR principles as well as data repository trust principles, on developing and sharing open source tools, providing exemplar applications, linking to other resources, and building community. So what do we have at this point? We have actually 32 data sets and growing, and I'm hoping before in the next 6 months, we'll have at least 6 very unique, valuable data sets coming on board, if not more. We have about 50,000 overnight polysomnograms, about 7,000 actigraphy files, and we've annotated over 14,000 terms, including about 5,000 with detailed provenance information. We've shared a couple of petabytes of data. We share about 2 terabytes a week. So this actually, if you go, this is a snapshot from our website, and you could see here's just a list of the different data sets, and these are 3 that were highlighted this week, and this just emphasizes the diversity. This is the Apples trial, which was a trial of sleep apnea. Here is a study on looking at opioid use agonists in non-human primates and sleep. And here is a study during pregnancy of sleep on the mother and fetus, but there are many others. And Dr. Ying Zhang in our group is always trying to help the user, and one of the tools that she's done is create a cohort matrix, so you could rapidly at a glance look across multiple data sets, and here are the initials of the different data sets along the left-hand side, and the different categories of data that are available. For example, if you wanted studies that had laboratory assays, you would look down this column. If you wanted studies that had anthropometry, you would look down that column. And as I mentioned, our data is only valuable as our metadata, and we also spend a really long time sort of standardizing our data dictionaries, the folder structures. So in any given database, we've organized our data by these folders like anthropometry, demographics, polysomnography, lifestyle, and one can search and again see detailed definitions for each of these. And we also have harmonized many of these variables across data sets. For example, when possible, we use the TopMed and Biodata Catalyst standards as well. And this is showing that we harmonize body mass index using this. We show the units, numerical, and for any given data set, you could, simply search and look at the distribution here of this variable and also see really what visits it was collected in. So in this case, it was all collected across multiple visits. And here for this group, I show here insulin from one data set, and this is the Hispanic Community Health Study. And you can see we have almost 14,000 fasting insulin measures, really, and it shows really the units and again in the processing. And if you like the sleep data, you could very simply, after creating an online data use agreement, download as many of the PSGs or polysomnograms that are useful, that is the raw signals, using a RubyGen. And just briefly here, I think this may not be a sleep audience, but I'll go through this very quickly. But Sean Purcell, as I mentioned, has created really powerful tools to address multiple really objectives. One is to really help with harmonizing sleep studies such that we have some core, or as he labels them, canonical channels, names across all studies, so you don't have to fight with the way different sleep labs may label things. And you also, we do a lot of data checking about things that are quite technical, but for a sleep researcher are important, like the polarity of the signals or any corruption, and we show what we can fix versus what we could flag. And again, one of the objectives is to provide really a framework for interpreting the data. To this date, there aren't great normative or reference-based data. So in fact, a lot of Sean's tools really allow individuals to see how any given study compares with other data, and ultimately to actually generate normative data and prediction equations. And Sean's latest tool is a bring your own data model, where you could actually upload your sleep data into something he calls using Moonbeam and an interactive viewer called Moonlight, and actually look through, your own data and do some online spectral analysis and other processing. And we also are very eager to outreach to the community, and I hope I'll hear from some of you as well. We do webinars. We're now planning our next webinar, which will all be about signals. Well, actually, I'm not sure which will come first. The two ones that are coming up, one is about the tools, the signal analysis tools, and the other is about animal data that we have in NSRR and that we hope to have soon. And we try to promote community through blogs and really, other video interaction. So one of the things that I know, there are basic scientists on this group, and one of the things we don't have in our data set is actually the genetic or the molecular data. However, we're working very closely with NHLBI's biodata catalyst, so that the data, the really deep sleep data, the signal data in NSRR can be easily linked with the genomics data and the imaging data in biodata catalyst. So we're in the process of formalizing our relationship with biodata catalyst. But until that's formalized, it is very possible to get cross-linked data. So one could go into dbGaP, for example, in TopMed, and link to our NSRR physiologic data. So let me now just spend a few minutes giving some examples of what a metabolic researcher might do using data within NSRR. Some of it would be, though, in all fairness, downloading data from dbGaP as well. So a very early study. Remember, I said one of the questions is the relationship of sleep, in this case, sleep apnea, and glucose regulation vary by race? So the multi-ethnic study of atherosclerosis, we had this data, and you could see, in fact, that moderate to severe apnea is more strongly associated with abnormal fasting glucose in African Americans and whites compared to Chinese and Hispanics. In another study, the Hispanic Community Health Study, we found that cross-sectionally, that sleep apnea was associated with hypertension, impaired fasting glucose or impaired glucose tolerance, and diabetes, even in analyses adjusted for obesity. And then in prospective analysis, you could see that sleep-disordered breathing was associated with both incident hypertension and diabetes, although insomnia was actually more strongly associated with hypertension and not significantly associated with incident diabetes. We also, in MESA, we're able to look at really the occurrence, both cross-sectionally and longitudinally, of developing multiple metabolic abnormalities. And in this time, we looked at sleep irregularity based on the actigraphy data I showed you. That is variability in sleep duration and sleep timing. And you could see that those who really had an increased amount of variability in their sleep were twofold more likely to develop multiple metabolic abnormalities over a 6 to 10 year period. And a very recent article that also came from Mesa really pursued the hypothesis that that the sleep EEG tells us something very important about brain function that's tied to metabolism. So here what you see is that a reduced amount of deep slow wave sleep, or what we call N3 sleep. As you remember, I said this is the stage where parasympathetic activity is high, sympathetic activity is low. It's a stage that is thought to be when there may be a coordination between a number of neurohumoral processes. So when that is reduced, you could see that in fact there is an increase hazard of developing type 2 diabetes over time. And again, this was also from the MESA study. And in fact, that relationship is somewhat nonlinear. So again, the likelihood of developing diabetes goes down quite dramatically, and 3 goes up. And here data from my colleague, Dr. using Hispanic community health data, and here what they did with Michael Elger is calculate the genetic correlations within sleep traits and in men and in women. And here you have this in a box. You'll see the correlations, the genetic correlations between traits like sleep duration, AHI, sleepiness, versus the correlation between these traits and other traits, including these clusters of glucose of glucose abnormalities. And what you could see, and the strength of the line is actually in proportion to the strength of the genetic correlation. What's very interesting, these genetic correlations are stronger for women than men. More correlations between sleep traits and glucose traits in women than men, suggesting that there are underlying risk factors, genetically determined risk factors for both sleep disturbances and glucose metabolism. So in addition to causal and associations, there's likely pleiotropic associations. And here's some work that my colleague Hemi Wang and Dr. Fakith are just preparing, also from Hispanic community health studies, simply looking at a trait called excessive sleepiness and doing a metabolomic analysis and showing that there are specific metabolites that are elevated in association with sleepiness, and some of them steroid hormones, cortisol and melatonin related pathways, tyrosine, sphygmomyelin, and a combination, and that some of these may reflect lifestyle or really metabolizing genes, but again, providing some really novel insights into how sleep may be connected to metabolism. And then almost finally, this is a paper that I think will come out very soon. And again, Dr. Sofer and Dr. Zhang did again Hispanic community health study where they actually looked at the multiple sleep traits from an overnight study and created a principal and reduced traits into 2 dimensions, which we call principal component 1, which is predominantly driven by overnight hypoxia severity, versus principal component 2, which is actually a trait we see particularly more in women that's associated with short events with a higher level of arousals. And from these 2 phenotypic principal components of summary measures, she created a metabolic risk score, actually really training or really doing a canonical correlation between these with multiple metabolites, which really are shown here in both men and women, and then taking both the metabolic risk score as well as the physiologic measures and comparing the extent to which they predict incident diabetes. And interestingly, The metabolic risk scores, not that were trained on the physiologic ones, better predict incident diabetes in men and women compared to just the simple physiologic risk factors. And many of these associations in a data set. And then now finally, this is from Dr. Walker's group at Berkeley. And they really have been very interested in interrogating the overnight EEG as a window into how synaptic function and thalamic cortical circuitry interact to influence a wide range of activities, including autonomic function. And in this case, they linked it to metabolism. So what they did was they looked at two of the NSRR databases. One was my very first data set that I created in 1990 that I share, my first RO1, long time ago, Cleveland Family Study, where we had glucose measures, glucose measured and after a 2-hour glucose tolerance test. And in the MESA study, where we just had glucose in the morning, both studies had sleep studies done. And then what they did was then they took the EEG-based data, looked at the coupling of what we call slow oscillations and spindles, which are measures of cortical thalamic circuitry, and looked at the timing of these spindles and slow wave oscillations, which neurophysiologists are very interested in, you know, as markers of, again, brain circuitry in general. And then also looked at the ECG signals to look at heart rate variability as an autonomic function, and then looked at our insulin glucose levels. And their conclusion in this article in Cell Reports was that there was an association between these brainwave signatures, that is the coupling of slow waves and spin next day glucose across two cohorts. They estimated that those associations were partially mediated by autonomic activity as measured by heart rate variability, and suggested that sleep may regulate glycemic status via insulin sensitivity, and that non-REM brain waves may be a glycemic biomarker. And this is just a little bit of their data. This shows how, you know, they link the wave oscillations here in black, and these are spindles. These, again, extracted from the nice ease is what we call a nice coupled response, and here is really an uncoupled response. And it was really the proportion of coupled slow waves that most strongly predicted next day both glucose and insulin. And again, they you know, they implicate that this coupling may tell us something about signaling of areas of the brain with the hypothalamus and then autonomic function. So what are the opportunities? So I'm hoping that I excited you about the importance of thinking about both macro and macro sleep architecture and its relationship to metabolism, and that these data that are in NSRR might help further understand the dynamic and system level crosstalk between multiple physiologic signals: sleep, breathing, oxygenation, heart rate, glucose. And I'm very excited because right now in MESA, I'm doing an ancillary study of sleep. At the same time, another group is doing an ancillary study of continuous glucose monitoring. So in the near future, we'll be able to link really, you know, continuous glucose monitoring with EEG data. And I want to suggest that also by linking data within NSRR to dbGaP at TopMed, there will be these opportunities to explore molecular pathways, as I mentioned, including the role of circadian rhythms and their relationship to transcriptomes and metabolic pathways, and use genetics to interrogate causality. And I want to just end by saying, you know, our data is only as useful as the data sets we have in NSRR, and you as metabolic researchers, I encourage you to contact us and think about sharing any of your data with NSRR should it have any sleep related variables, and we would be glad to meet with you and support you with that. So I'd like to take a few questions and acknowledge my the MPI, my co-director, Sean Purcell, who's really led this amazing signal analysis, as well as an incredible team of people that are listed here. So thank you, and I can now take questions.
Okay, thank you for Dr. Redline's presentation. So now is our Q&A session. You are welcome to unmute yourself to ask question, or use the chat function to ask question. Okay, the first question, do you know offhand how many individuals in the DB include data for dietary intake, genetics, gut microbiome, or related data?
It's a really good question. You know, as I said, within NSRR, we don't have genetics or microbiotic data, but there are some of those data that exist in TopMed and the primary cohorts. So in some cases, what research would do is apply, and then the data in the other resources and link them. Example, Hispanic community health example has the microbiota dietary intake data, and that cohort is 14,000 with sleep data, and about 2,600. That's the sleep apnea data. 26 actigraphy data. MESA also, you know, MESA, a number of the other cohorts have genetic data, and new mom to be, a pregnancy cohort, also has genetics data, and they and sleep data. So you know, I have to work a little bit through the cohorts, because they're, you know, again, some of the data are in other resources.
Okay, so our next question, along similar lines, are there data or substance use data?
Absolute studies that are looking at use. We have a study called Answers that are looking at suicidal. That's one study that we were my group, including Dr. Purcell and my colleague Dr. Wang, were just funded for a NIDDK initiative to live opioid use disorder, sleep, tree, NIDDK together will be to make.
I think from the previous question is coming from Barbara said, thank you, very helpful. It's useful to be reminded about potential link back to the TopMed and the original study data. And I think if you want to unmute yourself, right? So you raise your hand.
Yes, so I put some stuff in the chat and she can look at it later. The UNMH Sleep Center did a big presentation for a group called New Mexico Endocrinology. That's an endocrinology echo, and it's on every other Wednesday. And it would be helpful. She has a lot of data, and you may be able to get some by particular genetic groups, Native Americans versus Hispanic, which is kind of a crossover group. And I have a background in anthropology and genetics, so that's why I thought of that. The other issue as a nurse we saw is what time of day people take their actual blood pressure medicines can really knock out sleep because they're up using the bathroom. And we try to tell them, you know, take it this time of day, but if they forget and take it later, there's nothing I can do except tell them, well, we want your blood pressure under control. So yeah, so thank you. It's a wonderful program.
Thank you for those comments. And if you want to, if you had like a name of someone program, just a couple of things. We actually do have, again, one of the things we're doing in the current MESA study is actually getting timing of blood pressure medications, and also we'll be sharing ambulatory blood pressure. And I also see a comment or a question about non-REM latency. Absolutely. And in fact, you need to look at Luna Toolbox, which makes very easy metrics.
Okay, and we have another audience raise a hand. It's I think Dr. Elish Kumar.
Yes, yeah, thank you, Dr. Redline, for great presentation. You already answered my question about the REM latency. I also wanted to know if your data can be used, your data resource can be used to look at the REM behavioral disorders, like to qualify. Can we say that this particular individual is going to develop RBD?
Great. That's a very popular question. I mean, I actually review every data use agreement, and there's a lot of people interested in RBD. Clinical data sets from sleep labs in the data set with RBD diagnoses. And as you need signals at risk for RBD is the strength of the chin. People interested in RBD often extract that channel and then look at it in relationship to other subsequent health issues.
I see. How about EG coherence?
Coherence?
Yeah.
Yeah, so we haven't generated coherence measures, but Dr. Purcell's Luna toolkit, if it doesn't have it now, will have it in the future. Depending on your interests and skills, you could easily, based on the data we have, easily download. I mean, the data are, the EEG data, do your own coherence measures, but I think Dr. Purcell will probably now have it in the future.